That's what started morning when we were gathering when I was going to the okay, you can go out today. Okay. 8 o'clock when I will be. You know, it's okay, no need to come. Which day is that? 24th? Okay. When will we be coming back, Tomani? Is it for one day only? But, okay. Friday I have to hear duty. Good evening to all. I think my voice is also audible. I am Sandhya, a PMRF research scholar from IIT Kharagpur. Today in this live session, we will first discuss about the assignment 3 questions, followed by the summary of this week 4. Then we will solve few numericals corresponding to the week 4 data. Though this week 4 is mostly of a theoretical test, still we try to solve one or two numericals. I hope you all could have already submitted this week 3 assignment questions. So if you could see the first question, which type of aggregates, especially the igneous rocks of origin, they are asking has finer grains. So we know that uh, okay. So we have two types of rocks, as you all know. That is one is intrusive and another is extrusive. So how can we know that which has finer grains? Is one way is, for example, if you take the extrusive and intrusive, when the molten magma, whichever is formed beneath the earth, so if it gets solidified inside the earth itself, so yeah, so as the process is very slow solidification, you can see the grains can form bigger and bigger. But if you see the extrusive process where the magma comes outside and the solidification could be very quick, then you can see that the grains can be very finer in nature. So the finer particles would be in extrusive type of igneous rocks. And when it comes to the second question, quartzite is a derivative form of. So quartzite is actually a metamorphic rock, if you could see. So these metamorphic rocks usually formed either from the igneous rocks or sedimentary rocks due to the pressure or temperature formations. So you can see quartzite is either is it from the marble, granite, limestone or sandstone they are asking. So this is from sandstone. I think most of you could have already known this. And when it comes to the third question, which is true or false they are asking, primary crushers have less control on the shape of the aggregates or not. So basically we have two types of crushers. Yeah, yes, it is true. So basically we have two type of crushers. One is primary crushers. So basically when we have bigger, very bigger aggregates in the quarries, so we cannot directly use them to convert into our designated sizes. Our designated sizes are mostly 19, 13.2, 9.5 to till 75 micron. We need only these kind of sizes to be used in either BC gradation or DBM gradation. If you have very bigger rocks of 200 size, let us say, you cannot directly convert from 200 to 19 So in primary crushes, what happens is from bigger size to let us say 25 mm, you can reduce the aggregate sizes. When it comes to the secondary crushers, from the 25 mm, you can convert them into the designated sizes which are required. So the purpose of primary crushers is to reduce from higher sizes to the lower sizes. Here you do not have any control over the shape of the aggregates. When it comes to the secondary crushers, you will have a control over the shape and size. Let us say here, if you want to use the aggregates for SMA, here the requirement of shape could be different, and if you want to use for BC, the requirement of shape could be different. So this shape related controls can be done only in the secondary. So when I talk about the primary crushers, you might be already knowing that their jaw crushers are mostly the primary crushers. You could have seen in the video also. And the secondary crushers are like cone crushers. So here they are saying that primary crushers have less control. Yes, it is true. And the fourth question is, which of the following is are characteristic of slag aggregates? So, and is it only high water absorption? So usually, mm, slag aggregates are what? These are actually a waste material from the steel or metal plants. So those looks like a gray color if you could see the images and all. So their property is they have more water absorption. That is correct. But in addition to that, still people use the slag in the pavement industry because of their high skid resistance. So they have better skid resistance, but their water absorption is high. Even though few aggregates whose water absorption is high, as far as they satisfy all preliminary tests like impact tests and durability, all other tests, yeah. So, as far as when we say about skid resistance, we have methods to determine the skid resistance. One is polished stone value test, if you could have remembered. Otherwise, using HCl chloride also. These two tests, which we will be discussing in further slides also. In the last week summary, we have discussed, and this is already available in the video also. By using polished stone value, if you could have remembered in the video, we can calculate the skid resistance of the aggregates. Let us say if we have original aggregates, when the tire is moved on these aggregates, what is the resistance offered by these aggregates? Then we will subject these aggregates into too much of polishing. Then again we allow a tire to move over that. Then the difference between these two, the response between these two will be determined using polished stone value, which will be discussed in detail in the upcoming slide. Yeah, skid resistance means they are not more rough, they are rough enough so that the vehicle will not be skidding over the pavement surface when they are moving in the higher speeds. So skid resistance, too much of skid resistance is also is not recommended. So as per as the recommendations, the required amount of friction is allowed so that the vehicle will not skip. But being very low resistance of skid also is not allowed, because if there is no grip over the surface of the pavement, again they tend to slip. Especially the skid resistance is a problem when the wheel tire comes in contact with the water. On the dry surface, most all the pavements try to give some skid resistance. As far as when water is entered, let us say in the rainy season, we lost that friction between the tire and the pavement. So always we check for the skid resistance in presence of water in most of the conditions. What? Oh, it is actually not universal for all the countries, because this is a now using Merlin. If you could have, there are few tests like So if you could see, the Merlin is one of the equipment using which you can actually determine the resistance of the any pavement. In addition to that, especially for aggregates, if you want to determine what is their resistance, polystone value will be the one of the equipment. But in addition to this Merlin and polystone value, even on the pavement surface using laser technique also, in nowadays you can determine the skid resistance of the pavement surface. This all comes under the pavement management system. Polystone value is the only one test which will be detailed, in detail will be discussed, because this is especially as far as the aggregates are concerned. Remaining as far as the pavement surface is concerned, those tests will be discussed in detail in the upcoming classes. Okay. If you see the fifth question, this is also a very easiest question if you could have seen. Using the following table, calculate the cumulative percentage retained on 1.18 sieve. So you can see weight retained on each sieve size is given. We need to calculate the cumulative percentage retained on 1.18 sieve. So this is the weights already given. Cumulative, how do we get? For weights retained, 200 is a weight retained, 200 is a weight retained. So on 2.36, you know that 200 plus 150 will be 350. On 1.18, it will be the sum of all the weights retained from the top. So in the same way, you can calculate the cumulative weights retained. If you want to calculate the percentage, how do we calculate? So here for this, it will be, you have to calculate the total weight retained. Then this is the cumulative weight retained. So 200 by the total you can do, 350 by the 630 you can do. In the similar way you can calculate the cumulative weights retained. So they are asking for the cumulative weights retained on 1.18 C, which is 73.8%. And this one, if you see, so in the following table, identify the NMAS as per FHWA. So I know most of you have been asking in the mails that they have given the option wrong. Yes, so you can see the sieves I just mentioned are 19, 13.2 to 0.08, and they have given the percentage passing. So we know what is the NMAS. We need to calculate the percentage retained. So we need to calculate the percentage retained first. So if you know the 100% is the percent passing, then the percentage retained would be 100 minus 100. In the same way, you can do 100 minus 98 would be the percentage retained. So when you calculate this percentage retained, okay, someone is asking about previous question. Okay. So when you calculate the percentage retained, you can see that 9.5 mm sieve has the percentage retained of 13%. 13% is nothing but greater than 10%. So what is the meaning of NMAS? To calculate, to determine the NMAS, first we have to find out the sieve size. Which sieve size has more than 10% retained? Here 9.5 sieve has more than 10% retained. So 9.5 has more than 10% retained. So what is the sieve size just below that? 13.2. So NMAS would be 13.2. If we go to the previous question, as he was asking, yes. So in the previous question, what was being asked? What is the cumulative percentage retained on 1.18 sieve? So they have given all the weights retained on each sieve size. Let me calculate the cumulative. How do we calculate the cumulative? So if you can see here, weight retained on 4.75 is given as 200. So cumulative will be 200 only because there is no weight other than 200. If we come to the 2.36, weight retained is 150. So whatever is retained on 2.36 is 150 plus whatever is retained on 4.75, this also will retain on 2.36. So cumulative would be 200 plus 150, 350. In the similar way, you can do that. The weight retained on 1.18 will be 200 plus 150 plus 115, which is nothing but 465. So if you know the cumulative weights retained, now you have to calculate what is the percentage of cumulative retained. So if you could see, let me erase this. Okay, to calculate the cumulative retained, let us say here the cumulative retained is 200 divided by what is the total weight retained? 630 into 100. So this is your 31.7%. In the same way, if you come to the 1.18, what is the cumulative return? 465 out of 630 into 100, which is nothing but 73.8%. Okay. This question, how does bitumen interact with the active minerals on the aggregate's surface? C. It forms a hydrogen bond with aggregate minerals. B. Doesn't interact at all. C. Polar group of the bitumen forms salts of sodium, potassium, calcium, etc. Creates a strong polar interaction. So what usually happens when the bitumen interact with the aggregates? So let us say if we have a bitumen, what is the bitumen charge? Because of the hydroxy acids it contains, overall bitumen will be having a negative charge. So when it comes in contact with the aggregates, these aggregates can be of siliceous aggregates or calcium aggregates. Basically what happens, these acids will be reacting with the active minerals like sodium, potassium and calcium. Then they will be forming the salts of sodium, potassium, calcium, etc. So when these salts are formed, whenever water comes in contact with these salts, what happens? Salt is the one which can be soluble in the water. So these salts will be again soluble. That is the reason why whatever the bond already formed between bitumen and aggregate in the form of salts, it will be broken because of the presence of water. That is the reason why we need these salts, but those salts should be insoluble. They should not be dissolved in water. Sodium salts are always dissolved in water. Potassium salts are always dissolved in water. But calcium salts are not dissolved in water. That is the reason why wherever there is a moisture problem, moisture will be trying to break the bond between bitumen and aggregate. So what should we do in those cases? We need to add lime. When I say lime, lime is nothing but calcium oxide. So what does this calcium oxide do? This calcium oxide will react with the water and other moisture whatever is present, and the active minerals present there will be forming the salts with calcium. So those salts will be insoluble in water. That is how we will be reducing the moisture damage caused by the water in the bituminous mixture. So here if you see the option C, polar group of the bitumen. Polar group of the bitumen is nothing but the carboxylic or COOH functional groups. They form the salts of sodium, potassium, calcium and etc. So option C is the correct. And when it comes to the 8th question, the loss in addition between the aggregate and bitumen due to the suction created by moving tires is due to. So if you could see here, there are 4 mechanisms given as the options. What are these mechanisms are about? They are the mechanisms of adhesion. So adhesion is nothing but the bond between bitumen and aggregate, because these two are different molecules. Bitumen and bitumen will be same type of molecule. Then the bond between them will be called as cohesion. Okay. Here bitumen and aggregate are different type of molecules. So the bond between them is called as adhesion. So this adhesion will be broken when water comes in contact. How this adhesion will be broken? In using four mechanisms. These are the four mechanisms. First we need to understand what is the displacement of adhesion, detachment, hydraulic scoring and emulsification. Then we will be able to answer this suction created by moving tires is due to because of what. Okay. Let me show you through an image. So if you could see here, this is a bitumen and this is the aggregate. So bitumen and aggregate. So let us say here these are the voids. First what happens is water is coming in contact with these voids. Let us say these round things are water molecules. So initially what happens? Water is within the voids. Slowly what happens? This water will try to enter into the bitumen. Again it will again penetrate inside the bitumen. This process is called as diffusion. So by the process of diffusion, water will start entering from void to the bitumen. Then it will create the detachment or displacement of bitumen from this aggregate surface. This is the aggregate surface. So this is the aggregate surface. From this surface, this bitumen will be detached or displaced due to the process of diffusion. Okay. And if you take the emulsification, so let us say already this aggregate and bitumen is within the water saturated for so long. So diffusion is already happened and still the pavement is inside the water. So due to the long conditioning period in the water, because the pavement is stayed in water for so long, water started diffuses into the asphalt specimen. That is one thing. Then it will weaken the binder and it forms the water bitumen emulsion, which are unstable in water. Emulsion is usually what? Let us say you have the bitumen which is semi-solid in state. So this semi-solid bitumen, if you want to make it as a liquid, you will be calling that as emulsion. Usually how the bitumen will convert into emulsion? To liquid. First thing is either you have to increase the temperature so that this semi-solid bitumen can be converted into the liquid. Instead of increasing the temperature, still by adding some liquids, you can convert the bitumen into a liquid. So then the bitumen is called as emulsion. So here what they are saying is, because the bitumen is already saturated within the water for so long time, then it forms the bitumen emulsion within the water. It is kind of floating in the water. Bitumen with small particles will be floating in the water and the bond between the aggregates will be broken. So these are the two of the mechanism, and if you take third mechanism, which is nothing but the hydraulic scouring. So let us say there is a pavement already saturated within the water. When I say pavement, these are the aggregates. In between aggregates already bitumen is there. This is the pavement. So it is saturated with water. That means fully water it is saturated. Now there is a vehicle moving over that. That means this vehicle is applying the load over the saturated surface. So what happens when it applies a pressure? It can cause some abrasion of the binder from the aggregates and also can cause fine aggregates to become loose and dislodged from the pavement. So whatever the fine aggregates here, they can be dislodged from this compacted surface, or some of the bitumen can be abraded from the mixture. So this is due to the applied pressure from the traffic load to the saturated pavement surface. So this mechanism is called as hydraulic scouring. There can be another mechanism which is called as due to the pore pressure. Let us say now I have applied only one wheel load. There are repeated tire loads from morning to evening, let us say. Due to these repeated tire loads, what happens on the saturated pavements? Let us say this is the pavement and it is already saturated and you are applying a repeated load. So already these are aggregates from sides and the bottom there will be a subgrade. It is under pressure from the sides and you are also applying the load from the top. This internal pressure can cause the too much of pore pressure and erode the material and bitumen due to the water. This is due to the pore pressure. Now let us see what was being asked in the question. The loss in the addition between aggregate and bitumen due to the suction created by moving tires is due to. So they are saying that there is a pavement, it is already saturated and there is a vehicle and this vehicle is being applying the load. Because of this there is a suction created by moving tires. Suction means what? When the load is applied here, let us say higher pressure at the top, lower pressure at the bottom. So the suction is created at the bottom. So this is what causing the loss of the bitumen from the aggregate. So this mechanism is, it is not displacement and detachment, we know, because there is a moving wheel. So if you take the option C and D, this is not emulsification also, because emulsification is nothing but when the aggregate and bitumen is saturated inside the water for so long, the bitumen will be converted into the emulsion and it will be floating in the water, causing the disruption of that bitumen from the surface of aggregate. So if you take the hydraulic scoring where the saturated pavement, when the wheel loads are applied, that load will be applied on the bituminous mixture causing the suction and the water or bitumen which are being reacted for so long, then the part of the bitumen from the aggregate surface could be coming out, which is nothing but the breaking the bond of adhesion. Hydraulic scoring. The next question is, aggregate surface in presence of water is considered to have negative charge due to. So there is an aggregate and it has a negative charge. Because of what it has negative charge, they are saying. So let us say you have aggregate. Let me take the siliceous aggregate. Let us. So in the siliceous aggregate, what happens? SiO2, which is a siliceous aggregate. So they are saying, so initially what happens? There will be a moisture. Currently we are not talking about water. Aggregate has not come into contact with any kind of water. Currently there is a environmental moisture. So because of this moisture, what happens? This SiO2 will be converted into silanol group, SiOH, silanol group. When this SiOH comes into contact with water, what happens? This H plus will be pulled out. That means it depends upon the type of the water, whether you have acidic water or basic water. So let us not discuss about that. Let us say H plus is pulled out because you have a basic water, let us say. When the H plus is pulled out, what happens? Only SiO is remain. So this SiO negative has formed because of what? Because aggregate displacement of H plus ion from the aggregate atmosphere moisture bond. Is it because of this? Or displacement of OH? Is it because of this? Aggregate surface in presence of water is always basic. Definitely not this and not this. So the either it can be option A or option B. So displacement of H plus ion from the aggregate or the displacement of OH. It could be either A or B. So you have already seen from the solenoid group SiOH, H plus has been already taken out, because of which you are getting SiO minus, which is nothing but the negative charge on the aggregate. So let us see the summary of week 4. Then after that we will see few questions related to the week 4. Is there any questions corresponding to the week 3 assignment question? Does anyone have any doubt on week 3 question? Okay. Yes, you can unmute and ask, or you can type your question also. Okay. Hmm. Okay. So usually nominal maximum aggregate size. When do we call an aggregate size as NMAS is? Let us say you have 13.2, 9.5, 4.75. These are the three sizes available, let us say. Out of these sizes, yeah, I will go. Okay. If you see in this question, so they have given the percentage passing. Let us say these are the sieve sizes available and the percentage passing is already given. That means, let us say 19 mm sieve if you take, everything is passing 19 mm because they are saying 100% passing. And if you take 13.2, 98% are passing. That means 2% are retained. In the same way, it has been given for each sieve size. So we don't need all of that to understand. So percentage passing means this. 100% passing means everything is passing the 19 mm. So if I know the percentage passing, now I can calculate the percentage retained. If 100% is passing on 19 mm, that means there is nothing that has been retained on 19 mm, which implies 0% is retained. On 13.2, 98% is already passing. That means 2% is not passing, which is nothing but 2% is retained. In the same way, 87% is passing from the 9.5. When I say 87% is passing, that means out of 100 particles, 87 particles are passing. That means 13 particles are not passing, which is nothing but 13 particles are retained. So like that we can calculate for remaining all sizes. After calculating all these percentage retained, we need to see which percentage retained is more than 10. Let us say 95% is more than 10, 80 is more than 10, 70 is also more than 10, 40 is also more than 10, 13 is also more than 10. So out of all these more than 10, what is the first sieve which, whose percentage retained is more than 10? Already these are all more than 10, but 9.5 is the first sieve whose percentage retained is more than 10, which is nothing but 13% more than 10%. We need to identify that sieve first. The sieve whose percentage retained is more than 10. Let us say now I have identified that 9.5 is the sieve on which more than 10% is retained. So this is the first sieve to retain more than 10%. This is not the NMAS. We have identified 9.5 now. Now the sieve just earlier to that will be the NMAS. What is the sieve earlier to 9.5? Immediately earlier is 13.2. So this is what the NMAS. So in the same question, let us say if somebody asks what is MAS. MAS is nothing but maximum aggregate size. If you know the NMAS, here 13.2 is the NMAS. The sieve which is earlier to the NMAS will be the MAS. So here MAS will be 19 mm. Any doubt? I hope it must be clear now. So NMAS would be the sieve size. So before identifying the NMAS, we need to identify the sieve size on which minimum more than 10% is retained. So here 13%. Just before that sieve will be the 13.2. Okay. If we come to the week 4 lectures, so in all the 5 lectures, initially we have discussed about the aggregate shapes and the texture properties. Followed by we have discussed all the preliminary tests that has to be satisfied before selecting any aggregate. So here if you see morphology, which is nothing but the shape and texture characteristics of any aggregate. Why do we need to understand them? Because if the shape is irregular, then they will have better interlocking. If all the shapes are very round and smooth, you cannot get the better interlocking. If the interlocking is not there, stability will not be there. So for better stability, and if there is no better interlocking, when the load is applied at the top, these aggregates will be slipping from each other. If they are slipping means they will fail in the shear strength. So to have better stability, to have better shear strength, and also to have better moisture damage resistance. Moisture damage resistance, how do we get? If I have a smooth aggregate here, if I have a rough aggregate here, if I add bitumen to these, bitumen can coat well onto the rough aggregate because of the friction about the surface. If it is very smooth, the coating could not be proper. It will not be coming out of that. It has to get into the pores or irregularities and it should stick on the surface of the aggregate. That will be possible only with this irregular or rough textured aggregates. So if they are coating well, you can tell that moisture damage is avoided. And packing. Again, packing is nothing but the better interlocking. So this morphology talks about the shape and surface texture characteristics. These are required for stability, shear strength and moisture damage and packing. So as far as hot mix asphalts are concerned, angular and rough textured aggregates are preferred. Angular aggregates are preferred because we can have better interlocking so that stability, shear strength can be achieved. Packing can be well maintained. And when you talk about the rough textured aggregates, we prefer them because moisture damage can be avoided. But as far as the workability is concerned, workability means when I am mixing the aggregate with the bitumen, I should not require more energy to mix. It should be very easy to mix. But if you take very rough textured aggregates, it is difficult to mix easily. We need to give more energy. That is the reason why rounded aggregates are suitable for good workability. Rough aggregates are more suitable for moisture damage. But if you want to choose between workability and the performance of the pavement, we always go for performance. That is the reason why sometimes we may compromise on the workability, still we choose angular and rough textured aggregates. Okay, if you see the angular, they give the better interlocking, more internal friction and more stability. But if you take the rough textured aggregates, there will be more adhesion. When I say adhesion means that is the bond between aggregate and bitumen. So as far as the workability is concerned, angular aggregates are having more energy requirement and rounded aggregates are having less energy requirement. But what happens when the rounded aggregates are used, let us say, so it requires less energy. So with whatever less energy, it gets compacted well. So initially, intentionally, we keep, let us say, 7% of air voids in the pavement, so that when the vehicle starts moving, they themselves will be compacting, which is called as primary compaction. And after a particular number of years, there will be secondary compaction due to the vehicles. But if we use the rounded aggregates, initially, in the initial stages of pavement itself, it will be in the secondary compaction because it has been compacted well. If it is already in the secondary compaction, the moment heavier vehicle load comes, what happens? They will be showing rutting on the pavement surface. So that is the one of the reason why we avoid using rounded aggregates in the pavement construction. And if we consider the dense graded mixes, so dense graded mixes, here I have shown one photo which is BC2 gradation. If you could see, so these are the sizes used in the BC2 gradation, and this is the individual percentage retained. There is nothing retained on 19 mm, but if you could see on 13.2 you can see 5% is retained, and on 9.5 you can see something 16, 17, you can see the values here. But if you see the SMA is nothing but the gap graded mixture. So the difference between SMA and BC2 here you can observe is, in BC2 most of the fine particles, let us say less than 4.75, 2.36, 1.18, 600, 300, 150, 75 micron, and the dust here. So this dust, all the percentages are retained. That means you are including all these sizes materials. But if you come here, few of the finer sizes will be missing. In addition to that, most of the aggregate contribution is from the coarser aggregates. So if you want to talk about the gap graded mixtures, the angularity of coarse aggregates is sufficient. If you want to talk about the dense graded mixes like BC2 or 1, then you need to think about the fine aggregates angularity. So that is what I have mentioned here. So for dense graded, the fine aggregates angularity is more important because their amount is more, thereby they develop more internal friction. If you talk about open and gap graded mixtures, less fine aggregates are there, coarse aggregates are more, thereby the angularity of coarse aggregates is more important. Though we do not have a particular methods to determine the angularity of fine aggregates in India, but for coarse aggregates we do have the methods. In addition to that, one of the most important tests is shape characteristics, flakiness and elongation. This test might be very easy to perform, but as far as if we have more flaky and elongated particles in the mixtures, it really changes all your volumetrics, your entire optimum bitumen content, and your performance in the field will be completely different from the lab. So flakiness index, you can see here there are two apparatus. This is used to determine the flakiness. When I say flaky, if we have a aggregate like this, how flat it is. This is actually length. When I say flat, the thickness, how thinner it is. We do not want the metal to be very thin because if they are very thin, they will be broken. So that thinner size we will try to pass through this gap. If they are passing through this gap from top to bottom, that means they are very thin. So these are the slots provided to check. So each slot is for each size. Let us say this slot will be, here it will be written as 63 to 50. That means, so this thickness T will be 63 plus 50 by 2 into 0.6, as I mentioned, 0.6 times of average size. So in this slot, if your individual aggregate is passing, then you can say that yes, my aggregate is very flat, very thin. Like that, we have to separate all the aggregates corresponding to their sizes. Then we try to pass them through this. Then we determine Whatever is passing, we call them as flaky aggregates. Whatever is not passing, we call them as non-flaky aggregates. So what is the problem with these flaky aggregates? Why can't I use them? First thing is, if I have 3-4 flaky aggregates, let us say you have mixed with bitumen, now you have applied some vertical load from top. The moment you apply load, what happens is, they just gets compacted like that. They will not reorient or they will not be dislocated. They will just compact as it is. They lock up very easily. There won't be any orientation. But we need a better orientation to fill the gaps, because it will be providing, let us say if you have single aggregate here and it has 5 aggregates or 6 aggregates in contact. If a wheel load comes from top, then let us say 20 kilonewtons of wheel load. This 20 kilonewtons of wheel load will be now shared by 1, 2, 3, 4, 5, 6, 6 aggregates. Because all these are in contact, the load can be shared by 6 aggregates. If there is no load proper contact, this 20 kilonewton should be shared by either 2 or 3. Then what happens? Because 3 aggregates are sharing more load, they will be broken very easily. So having no orientation and locking up very easily is a main problem. In addition to that, because they are very flat, they are very thin, when the load is applied, they can be broken very easily. And the same is the disadvantage as you see for the elongated materials also. You can see this is the elongation gauge. So in the same way, here it will be written 6350, and this length will be 1.8 into 63 plus 50 by 2. So we take each aggregate, individual aggregates, we will try to place here. If this aggregate is stopped here, that means this aggregate's length is more than the slot provided. That means this aggregate is a long aggregate, elongated aggregate. We do not want the aggregates to be very long, because same disadvantage. They will not be oriented properly, they will lock up easily, and they will tend to break very easily. So this length would be greater than 1.8. They don't have any proper orientation, poor interlocking, easy breakage. So we calculate this flakiness index separately and elongation index separately. Then we combine them. We call that as combined flakiness and elongation index. So this is what we do in India according to the IS 2386. But as far as the American standards are considered, you can see here, this is actually the aggregate. If any aggregate you have taken, each aggregate will have length, width and thickness. So this is the length, this is the thickness and this is the width. So based upon the ratio of length to thickness, based upon the ratio of length to width, and also I have mentioned here, you can see, based on the ratio of width to thickness, length to width and length to thickness. That means by considering any two dimensions, you can calculate only flat aggregates. If I have 200 pieces of aggregates, out of 200, which are only flat, which are only elongated, or which are both flat and elongated can be determined. How do we determine? So this is the apparatus here, you can see. So this is actually fixed. This will be like a screw. This is also fixed screw. So you keep your apparatus here. So here gap would be always more. Here the gap will be small. So initially we take one aggregate. So this is the length of the aggregate. So I keep my aggregate like this along the length side. So when I keep here along the length side, this is actually a arm, this is a moving arm, you can actually move and rotate. So when you keep the aggregate here, when you fix this here, there will be a gap formed. When you fix the length here, there will be particular gap formed. So immediately, without disturbing this position, you will take this aggregate out and try to pass in this direction along the thickness direction. If this is passing through that direction, that means this aggregate is called as both flat and elongated. So this is the length, this is the thickness. So length to thickness is 5:1. What does that mean is, if let us say I have taken one aggregate its length is 5 mm, let us say, thickness is 1 mm. So your length is 5 times than the thickness. If any aggregate is having length of 5 times than the thickness, we call that aggregate as both flat and elongated according to the American standards. So in that process also you can still calculate only flat aggregates, only elongated aggregates. But this is one of the way to calculate both flat and elongated at a time. Only flat if you want to calculate. So here actually along the length I have fixed, right? Usually you should not fix along the length. You have to fix the aggregate along the width. So after fixing here along the width, let me erase this. So here you may need to fix along the width. When you fix the aggregate here along the width, there will be a gap formed here. Then, so width is fixed. Then along the thickness side, that means smallest dimension side, you try to pass. If it is passing, then you can say that that aggregate is flat. In the same way, we can calculate the elongated aggregates also. So we will mostly be not doing, but we still have this apparatus at IIT Kharagpur. We do for laboratory purposes, but still in India, as far as the preliminary tests are concerned, we do according to the IS 2386 of flakiness and elongation. And in addition to that, we have angularity test. As we have discussed already, for dense graded mixes, the angularity requirement is different. For gap graded and open graded, angularity is different. How do we actually determine the angularity of any aggregates? So one of the basic theory is, if you have rounded aggregates, and if you arrange them in any volume, that volume can be of 200 centimeter cube or 2000 whatever. Let us say I have a box here. I have filled entire box with the rounded aggregates. Anytime if you place rounded aggregates and fill, the amount of air voids or gaps formed by those rounded aggregates would always be 33%. Okay. So if anytime if your voids are more than 33%, let us say 35%, that means all of your aggregates are not rounded. There must be some aggregates which are not rounded. Let us say here the difference is 2%. That means there is the air voids extra of 2%. That must be because of the angular aggregates present. Because angular aggregates gives more air voids than the rounded aggregates. Based on this theory, so we always calculate the air voids. Air voids in excess to the 33%. So other than 33%, whatever extra air voids is, that is the indication of angularity. Okay. And we have another test called particle index test. So this is actually to understand the effect of shape and texture at a time. So this is actually an empirical test. So there is an empirical equation available. Let us say you can see here. So in this empirical equation, V10, V50 are the air voids. Okay. So we take a set of aggregates and we try to give 10 blows at a time. Then we calculate what is the voids present. Again for the same aggregates, we compact or give blows again. This time we give 50 blows. Then we calculate the voids again. So based on that, the empirical equation gives the particle index. Particle index. Don't confuse with the plasticity index. So particle index, if that value is based on that value, directly you can tell the given aggregate is either rounded or angular and rough textured. So you can see the values here. What we can understand is, if the particle index value is 6 to 7, that means air voids are lesser. We know that air voids are lesser means that is a rounded aggregate. If the particle index value is increasing to 15 to 20, that means more air voids are there. That means that aggregate could be angular or rough textured. So that's how, based upon the particle index, we can actually say whether the given amount of aggregates are round or angular. And another important property of the aggregate is surface area. So this surface area is always useful to calculate the bitumen film thickness. Why do we actually need to understand the bitumen film thickness is, so when we actually move to this volumetrics in upcoming lectures, we will understand the importance of that. Let us say, so you have already designed the mix, you have aggregate. So around this aggregate, there must be a bitumen coated. So this coating of the bitumen is different in dense graded mixtures. In the same aggregate, if you take in the gap or open graded, you can see there will be more thickness around the aggregate. So this higher thickness advantage is, higher the thickness, that means when water comes into contact, what happens? It cannot break this bond between the aggregate and bitumen. Thereby moisture damage can be avoided. So to avoid the moisture damage, we always prefer higher film thickness. But bitumen is not a cheap material, it is a costly material. So just because it is giving the higher moisture resistance, we cannot keep adding the bitumen. So we need to have sufficient amount of bitumen. You should not add too much, because having more higher content of bitumen also will cause the mix very smooth and soft. When the vehicle moves over the top of that smooth and soft mixture, what happens again? Rutting will be a problem. So we want an optimum bitumen, but the film thickness should be sufficient enough. So how do we confirm before finalizing the mix design is, we calculate this film thickness. How do we calculate? So you want this thickness. If we know the volume, if you know the area. Thickness, how do we get? Volume by area. Let us say volume equal to meter cube, area is meter square. So you will get meters, which is nothing but the thickness. That is a simple concept. So film thickness, to calculate the film thickness, you need the volume of the bitumen. This volume is actually coated over the aggregate surface. So surface area of aggregate is required, and the volume of bitumen that is being added. So this bitumen volume, how to calculate, that you will understand in the upcoming lectures. Let us say somebody has given the bitumen volume. Now you have to calculate the surface area of the aggregate. Then you can calculate the film thickness. So you can see these are the set of surface area factors. How to calculate this surface area? Is there anyone asking any question? Yeah, yeah, please. Hmm. Hmm. Okay. Usually, this assignment submissions will be not in the hands of the professor also. NPTEL team will be deciding. We might need to, if you want to request, you might need to write a mail to the team. Okay. And these lectures can be downloaded from the YouTube. I think we have already shared the link. Okay. Okay. If you have any request regarding the assignments, you need to send a mail to the NPTEL team. Okay. So if you could see here, these are the surface area factors. I will explain what is surface area factor and how to usually calculate. So as far as the surface area calculation is considered, so you need to know only the surface area of sphere and cube, because we assume that the aggregates are either in spherical shape or in cubical in shape. So how to calculate the surface area factor is, let us say now we have individual aggregate. So we know that specific gravity is density of the material by density of water. Let us say density of water is 1. Okay, so I am not considering this density of water because that is 1. So whatever at the top will be density of the material. What is the density? Density is nothing but this weight by volume. So surface area of individual aggregate if you want to calculate. So when I say area, how do we get? From the specific gravity, weight by volume. So let me bring this volume to this side. Then you have weight by specific gravity. Volume can be written as area into diameter, because we are assuming a spherical or cubical. So weight by G. So now you need specific surface area. So weight by G into D. See, that is how you got this formula of weight by specific gravity into D. So this is for individual aggregate. Okay. You might have so many aggregates. So this is for individual aggregate. Let us say you have 1 kg of aggregates now. So for one aggregate, the surface area is 1 meter square, let us say. You have 1 kg. So in that 1 kg, how many meter square of surface areas are there? If I have 10 aggregates, 10 meter square, let us say, per kg. So this is what called as surface area factor. So when you are calculating for a set of aggregates, if we have this surface area factor, the surface area factor indicates that total surface area of those aggregates, then you have to multiply with the percentage. Let us say you have 100 aggregates number into their surface area factor, then you will get the total surface area. We will solve a question, then you will understand. Let us see here. So calculate the total surface area of the mixture if the bulk specific gravity is 2.670. So G has been given. So to calculate the surface area, first you have to calculate surface area factor, then you have to multiply it with the weight of the aggregates. Okay. So weight of the aggregates already given. So first you need to calculate the surface area factor. Then you have to multiply these two. Then you will get the surface area of each aggregate. Then you can add all of them. Then you will get the total surface area. Okay, you can see here. So how to calculate this surface area factor? Okay, this is already given. How to calculate the surface area factor? I have told this is a meter square per kg. That means surface area of that particle out of total kg. Okay. So from the previous equation already surface area is okay. So surface area of sphere or cube you can do for anything, because both of them the ratio will be same. Pi d square is the surface area. Pi d cube by 6 will be the volume. So this is the area by volume. So how much you will get? 6 by d. Okay. Pi will be cancelled. So this is 6 by d. So now if you want meter square per kg. Okay. So from this specific gravity, you know weight by volume. Okay. So if you take the specific gravity to this side from the specific gravity, so volume equal to weight by specific gravity. Let me write specific gravity as G always, weight by G. Okay. So in this area by volume, instead of this volume, I will substitute this W by G by G. So you can take this to this side. Finally, you will get 6W by G D. So you don't need to remember the derivation all the time. So this is because directly given in the your discussion in the video. So I have been explained how it has come. Okay. So surface area factor, every time if you want to calculate, the formula is 6W by GD. So if you know this formula, let us take 19 mmc. How to calculate the surface area factor? 6 into, what is the weight? 500 divided by G is given in the formula, in the equation, 2.670 into D means size. What is the size? 19. So if you calculate that, you will get the surface area factor. Okay, you can multiply with this weight, you will get the total surface area. So if you calculate all the surface areas and if you add them, that is what the total surface area. So in problems they may ask you to do for 3 sizes or 2 sizes, they can give anything. And the next important preliminary test is aggregate impact test. So when I say impact means I am applying a sudden load onto the pavement. It can be aggregate or a combination of aggregate or mixture, because here we are going to check the quality of aggregate. So when I apply the sudden impact load, that energy will be absorbed by the aggregates. So some aggregates will break and they become into the small pieces because they are not that much tough enough. So if they are tough enough, they will not be broken into small pieces. So this impact test is to understand the toughness of the material and how resistant they are from the degradation. So what do? We take the aggregates which are passing from 12.5 retained on 10 mm. Then we will apply 15 blows on that. After that you can see there are small pieces degraded. So you will take the 2.36C, all these small pieces will be sieved. Whatever dust is there, that will be passed. Whatever bigger than 2.36, that will be retained. So now we calculate this amount. Let us say I have taken 500 grams, 200 grams is passing, then 200 by 500 into 100. So 40% is my aggregate impact value test. So if this value is more, that means more amount is passing. That means more amount is becoming into small pieces. That means this aggregate is not that much strong. So aggregate impact value should be as low as possible. You should not be very high. And in the same way, if you see the Los Angeles abrasion test, so this is to understand the abrasion resistance. What do you mean by abrasion? So when two materials, let us say this is one aggregate, another aggregate, if they both rub each other, you can see there is a dust formed. That is what called abrasion. So how resistant these two particles are against this abrasion. So here not the aggregates always. One can be aggregate, another can be wheel tire from the top. So wheel will be moving front and forward and backward. Then what is the abrasion resistance here? To understand that, so the abrasion between the tire and road, to understand that you need to perform some abrasion resistance test. Los Angeles abrasion value is one of the tests. So it actually indicates the dust. So when you perform this test, what you will see, let us say these are the aggregate particles and these are the actual steel balls. Why did we input the steel balls? These steel balls induce some abrasion. That means artificially you are giving So when you are rotating this drum, what happens? These aggregates and the steel balls will come into contact, and then aggregates will be broken into small pieces. That means these abrasive charges are nothing but from the steel balls. They induce artificial abrasion. Okay, so this artificial abrasion will be applied. So that we will apply for 20 to 33 revolutions. So how many steel balls we will select, and how much time we will do this, all this depends upon type of gradation. So that I will show in the next slide what is the type of gradation. So based on that we choose the type of gradation, number of revolutions and number of steel balls. Then we rotate the drum. Then what happens? After doing that, there will be a lot of aggregate which will become into the small pieces or dust. Then you take 1.7 mm sieve, try to put all the material here and sieve. There will be some dust that would be passing below. So let us say again, this is 300 grams you have taken, 100 grams has already passed. That means 100 by 300 into 100. That means around 33% is your Los Angeles abrasion value. So here also we want the value to be as low as possible. Okay. So I was talking about the selection of gradations, right? So you can see here, these are the sieve sizes starting from 80 to 4.75, and this is the range. That means aggregate passing 80 and retain at 63. Okay. So you have to select either A, B, C, D, E, F, G. These are the type of gradations. Let us say if I select grade A, what happens? If you select grade A, then you need to take aggregates of these sizes. That means, so if you have aggregates of different sizes with you, now you don't know on which sizes you have to perform this test. If you choose A, what they tell is you choose 40 mm sieve and you choose 25 mm sieve. So according to these two, you choose 40 mm sieve and 25 mm sieve, pass the material. So they should pass through 40 and they should retain on 25. Like that you take around 1.2 kg. In the same way, next time you take 25 mm sieve, 20 mm sieve, try to pass the material from 25. They will be, some material will be retained on 20. Like that you collect around 1.2 kg. In the same way, 20 to 12.5, 12.5 to 10. So these four combinations of each 1.2 kg you take. Along with that, you add the steel balls. Then you do the revolutions of 20 to 30 revolutions per minute. At the end, sieve the material from 1.7 mm. See how much material is actually passing. Based on that, we can tell what is the Los Angeles abrasion value. So that was Los Angeles abrasion. So in addition to that, there is another test called micro Debel abrasion test. So the difference between these two is, in the previous Los Angeles abrasion, you are going to break the aggregate into smaller sizes. Okay. But here you are going to polish the aggregate. That means if the aggregate is like this, when you polish means you are rubbing, polishing means you are making into smooth. That is, if there is a rough aggregate, you are polishing and making into very flat or smooth. So Los Angeles abrasion breaks the aggregates, whereas the Devil abrasion polishes the aggregates. So here extra thing is steel charges of 5 kg. Along with that you also add water. In Los Angeles abrasion, only aggregates and the steel charges are rotated. But here water also will be added. How many rotations you will be doing depends upon the again size of aggregates chosen. How much time you do, that also depends upon the size. At the end, whatever the material has come, you try to sieve with 1.18 mm sieve and then see how much is passing, then calculate the percentage, and that percentage should be as low as possible. And as I told, So you have to select a type of the gradation. If you select, let us say, gradation C, then you have to select 8 steel balls, and those 8 steel balls size will be around 3330 plus or minus 20. So in addition to that, there is another test which is nothing but the durability and soundness. So this test is actually useful if you want to understand the moisture damage of the aggregates. Durability and soundness. So nothing but how durable, if you buy any material, how durable it will be under the action of water. Let us say here the material is aggregate. So when the aggregate is subjected to so much of water, how many days it can withstand strongly to the traffic load. So this is to understand the resistance to wetting and drying. So sometimes it can be rainy season, after that it can be summer, again it will be rainy season, and in colder regions it can be freezing and thawing. Okay, on these conditions how resistant the aggregates are, to understand that we do this durability and soundness test. What do we do for that? We have to create one solution. Why do we prepare a solution? Because now you have an aggregate. You want to artificially degrade this aggregate. So you need to find a solution. When I say solution, that means chemical solution. So this solution, if you put the aggregate into the solution, this aggregate has to degrade. It has to get dissolved. Like that you have to prepare some solution. Here sodium sulfate or magnesium sulfate is that kind of solution. So we keep the aggregates into the solution for around 16 to 18 hours. After 18 hours, I will take that aggregates out. I will take some sieve, then I will drain. What happened? All the solution will be passed out, only aggregates will be here. Then I will keep these aggregates into oven. So what am I doing here? When I am keeping the aggregates into solution, I am wetting the aggregates. When I am keeping the aggregates into oven, I am drying the aggregates. So this wetting and drying action I am artificially simulating in the laboratory. So after keeping in the oven, I will take them out and I will take the weight. So there must be some initial weight. After this wetting and drying, weight will be decreased or changed. So what is the change in weight? That I will observe, let us say first time. Again, from the oven, I will take the material, again I will keep in the solution, then again after 16 to 18 hours, I will take that out, I will drain from the sieve, then I will keep in the oven, again I will take the weight. Like that I have to repeat for around 5 cycles. Then what is the loss in weight after these 5 cycles is what we have to calculate. So you can either use sodium sulfate or magnesium sulfate. If you use the sodium sulfate, you must be calculating the loss in weight. Let us say initially it is 100 grams. After 5 cycles, it has become 80 grams. That means 20 grams is less. That means 20% is loss. So loss should be always less than 12% for sodium sulfate, should be always less than 18% for magnesium sulfate. So depending upon the type of solution you are using. But as far as this experiment is considered, so you are trying to take the aggregate and keeping into the solution and see whether it can be dissolved or not. But why do we do this mainly? If you see the colder regions like Jammu Kashmir, what happens? Let us say there are aggregates. So in rainy season, there enters some water inside these aggregates. So what happens suddenly due to the cold weather? This water here converts into snow or ice. So it becomes very stiff. When really sunny time comes or summer comes, what happens? That again will be converted into water. So this process is called freezing. When the ice is formed, that is called freezing. When the water is formed, that is called thawing. So this freezing and thawing action also we wanted to simulate in the lab. When I put this aggregate into the solution, This aggregate surface will be reacted with the solution and also forms salts. So this salts is an indication of formation of ice. Okay. But in reality what happens? We are not directly using the aggregates in the construction. We are actually mixing this with the bitumen. So all the aggregates are now coated with the bitumen. So there is less possibility that these aggregates will be subjected to the water directly. So that is the reason why this durability or soundness experiment doesn't have much implication to the field performance, because this formation of ice is very rare, especially when the aggregates are already coated with bitumen. Okay, so let us say in some cases we usually 2% is the maximum water absorption we allow for the aggregates. Let us say if you have slag aggregates, those kind of aggregates where water absorption is more than 2%. So in those cases, there could be a possibility of this. So in those cases, you can perform this test. Otherwise, for normal conditions, it is not suggested to use this soundness test. Okay. And another part is the clay or deleterious material. So if you have fine aggregate, when I say fine aggregate, passing 75 micron. So in that fine aggregate, there will be some dust. So dust or clay, let us say. So what is the quality of that clay? That means we cannot avoid this clay or dust from the aggregates. There will be existence of some dust. So how what is the quality of that? What is the plasticity nature? Because we do not want this clay or dust to be more plastic, because then it will absorb more water. It will cause the problems in the subgrade also. So to quantify the fine dust, so especially we take the fine means less than 4.75 and less than 2.36, 1.18 and all those. So we take that fine aggregate, we immerse them into some solution. This solution is prepared using calcium chloride and glycerin. So there is a bottle kind of thing like this, plastic one. So inside this you keep the solution, then you will add your fine aggregate, then you will shake this bottle. After shaking, you will keep this bottle without disturbing for around 20 minutes. Then you can actually see till here, let us say your fine aggregate will be there. Top of that you can see there will be some clay that is being separated. So based on the height of this clay form, you can calculate the sand equivalent value. So this test is usually to understand the quality of the clay. So in addition to the sand equivalent test, you can also perform liquid limit and plastic limit. This we already know, right? Liquid limit, plastic limit test, how to perform on soils, which we have already discussed. This is actually on 425 micron passing sieve. So this is a measure of plasticity of the clay. So we recommend that this plasticity should be always less than 4. And in addition to that, there is another test called methyl blue test. This is the test actually more reliable test to be discussed. Let us say you have 10 grams of sample. So you first initially you have to prepare some suspension. Suspension is nothing but some, if you have a soil, you cannot use directly like a solid soil. So you are adding with some distilled water. So 10 grams of soil, 30 grams of distilled water. Now you call that as suspension. That means in the distilled water, your soil is floating like this. And second thing is you have to prepare a solution. So methylene blue is a chemical, let us say. You have to add distilled water to that. Then you prepare 200 ml of that solution. Now you have 200 ml of methylene blue. You have a soil suspension. Now what you have to do is, this is your soil suspension. You start adding this methylene blue solution 0.5 ml. Initially add 0.5 ml. This is called titration process. When you add 0.5 ml, this 0.5 ml methylene blue will come and interact with the soil suspension. Now take one drop of that, place on a filter paper. I will show the picture in the next slide. Let us say like this, you place a drop here. So now what will we do? Again start adding another 0.5 ml of methylene blue. Then again take a drop, put on the filter paper. Like that you keep adding the each 0.5 ml. So what you will observe is initially there will be only dark brown circle. As the amount of methylene blue added is increased, you will see that around this dark brown there will be a blue color circle formed. That implies that this methylene blue is actually trying to interact with the existing soil suspension. Initially, whatever the methylene blue you have added is not sufficient. That's why this blue color circle is not formed. Here when you see this blue color circle, then you can stop the test. So, if the requirement, in order to see this blue color circle, if you have to add too much of methylene blue, that means there is a lot of clay present. If you could see this methylene blue color circle here itself, that means with less 0.5 mb methylene blue itself you could see, that means the clay content is very less, that means the good quality. So this methylene blue is proportional to the clay content and its specific surface area of the clay. So after conducting the experiment, let us say lower is a methylene blue value that is desirable, let us say 5 to 6. If we have more than 20, that means that is a failed condition of the soil. We are not supposed to use that one. And it is an indicator of moisture susceptibility. So if we have an aggregate, if there is a lot of dust around that aggregate, it will not allow your bitumen to come and coat properly. When there is no proper coating, what happens? When water comes into contact, it is very easy for the water to remove this bitumen from the aggregate surface, which is nothing but the moisture damage. We need to avoid that. And the most important is this specific gravity. Okay, most of the people might have already known about this. Specific gravity is nothing but, so if you want to calculate specific gravity of any material, density of that material divided by density of water. So how much is the weight of any material in comparison with the water? To say simply, let us say if I say specific gravity is 2.72, that means my material is 2.72 times heavier than the water. That is what usually the specific gravity means. So weight of a unit volume of water. Let us say you have an aggregate in the air. This weight by weight of an equal volume of water at 23. So this aggregate is occupying this much volume. So now what I will do is, in the same volume, if I put the water, how much will be the weight of that water? So that is what the denominator. So weight of aggregate by weight of water in that particular volume is what called as the specific gravity. So that we have actually represented in terms of buoyant force and all, you can write in any form. Here the main difference is we have to understand the difference between the specific gravities. There are three different kinds of specific gravities. Before explaining, let me show you this image and explain. Let us say this grey color one is the aggregate. Okay. This is actually the real aggregate. So if you actually take this aggregate and put it in water, what happens? Like this, in the gaps, water will be filled. So now what is the volume of this aggregate? Now the volume of aggregate is entire this, because already this is the solid. In addition to that, these pores are now filled with water. So now the volume will be entire this total. Okay. So if you consider the volume of aggregate as this entire total, that volume is called as bulk volume. So if you consider this bulk volume in the calculation, that specific gravity is called as bulk specific gravity. Let us say you have taken aggregate volume as only this. Let us say this only this outer surface. You have not immersed the aggregate into water, only this outer surface. That is called as volume of solids. If you use the volume of only solids, we call that as apparent specific gravity. Apparent means not real. This is not the real. Because if you go and keep this aggregate into water, it will absorb some water into these gaps. But we are not considering that volume. We are considering only the outer volume. That's why that specific gravity is apparent. But if you consider entire, that is bulk. So there are three types of specific gravities. First I will explain this apparent and bulk, then we can discuss about the effective. So one is the bulk specific gravity, another is the apparent. So in the bulk specific gravity, we consider total volume. In the apparent specific gravity, we consider only water permeable voids. So that means, so you have taken only the outer surface. Within this aggregate, there must be some voids that you don't know. But these remaining you have not considered. That is the apparent. So there is another called as effective specific gravity. So what volume we consider here? Let us say if you see the image here. So this is actually the aggregate surface and voids are filled with water. If you take entire boundary, you call it as bulk. If you take only this, you call it as solids. So sometimes what happens is, this whatever is there, these voids, this blue color is actually water filled. Sometimes what happened is, half of that might be filled with bitumen. Okay, some voids can be filled with bitumen. Let us say till this bitumen is filled. Remaining void it cannot able to go and fill because bitumen is viscous in nature. So like water it cannot flow very easily. So it could able to fill only this part. It can't go inside. Okay. So now what volume I want is, I want the volume that is not filled with bitumen. So that means usually I want this surface. So this solid, and in addition to the solid, this part which is not filled with the bitumen. So that is the volume we have to consider. That is what called as effective specific gravity. But it is extremely difficult to calculate the effective specific gravity. You can see in this image. See, this is the aggregate. This is the void filled with water. This is the void filled with bitumen. So those voids that are not filled with bitumen, we need to calculate so that we can calculate the effective specific gravity. But in the laboratory, it is very difficult to calculate that. That is the reason why bulk and apparent specific gravity are the ones which we calculate in this laboratory. Effective specific gravity cannot be calculated in the laboratory. So usually how do we calculate the specific gravity? Specific gravity can be calculated for coarse aggregate separately, fine aggregate separately, and filler. When I say coarse aggregate, those which are retained on 4.75. When I say fine aggregate, those which are passing 4.75. When I say filler, the material which is passing 75 micron. For those materials which are retained on 4.75 coarse aggregates, directly we take the 5 kg of the material, we immerse them in the 24 hours. So what happens when I immerse them in the 24 hours? So initially this is aggregate. When I immerse in the water like this, all the pores will be filled with water. Then I will take them out. If any water is there on this surface, I will wipe with the towel. Then whatever is inside the voids, I am okay with that. So I will wipe this surface. Then I will take the weight. That weight I call it as saturated surface dry weight. Then after that, I will keep this aggregate in the water. Then I will take the weight in water. After wiping that clearly, I keep in the oven, take that weight also. So these information is required to calculate the bulk specific gravity. So using the same information, you can actually calculate the apparent also, because to calculate the apparent specific gravity, you don't need this SSD weight. Directly using this, you can calculate. So these are the formulas given. But as far as fine aggregates are concerned, it is not that easy to calculate the specific gravity. Why? Let us say you have fine aggregate this. This is normal weight, dry weight. So dry weight is easy to calculate. Okay. I have already soaked them into the water for 24 hours, let us say. Now I will take a towel or a filter paper. I will wipe this fine aggregates. As I am keeping them as a separate individual particles, but fine aggregates, let us say, of 150 mm, 300 mm, sorry, below 1.18, 300, 600 and 300 and 75 micron. These sizes are not like individual particles. They look like some dust kind powder. So you cannot wipe them with some cover or paper or towel. That is impossible. Like in coarse aggregates, it is very easy to wipe. If you cannot wipe properly, then you cannot calculate your saturated surface dry. So how do we say what is the saturated surface dry weight for fine aggregate? That is the most difficulty everybody faces in the laboratory to calculate the specific gravity of fine aggregates. So for that, each person's have their own way of calculating SSD. As far as standard is concerned, so if you have 1 kg of material and if you soak it for 24 hours in water, so then you can say that they have absorbed all the water. Now you have to take that amount from the soaked aggregates. You have to expose them to some warm air. Like it should not be very warm. Like aggregate should not be very dry. It still looks like a moist in condition, but it should be dry. How do we know that? There will be a cone test. So just like a concrete slump test. So you fill the fine aggregates into this cone, you apply few blows, then you remove this cone. After removing the cone, your material should not be exactly like a fine shape. There should be some slump. It should fall off. That means that is in the SSD condition. If that is in that condition, take the weight, then that is called SSD weight. Then picrometer plus SSD plus water weight. Then oven dry that SSD weight, calculate that. So the formula will be given. Here the only difficulty which we face is using this cone. How do we finalize this condition? Because for each person in different stages, you feel like it is in SSD condition. If anything goes wrong, usually what happens is specific gravity has very much effect on your volumetrics. So it causes a lot of changes in the volumetrics. There is one question. It is a very quick question. So what was asked in the question? There is a stockpile A, stockpile B and C. In the stock A, there is 70% coarse aggregates are there and the specific gravity is given. And in the stockpile B, 50% coarse aggregates are there and 10% fine aggregates are there. Specific gravities are given. And in the stockpile C, only coarse aggregates are there of 30% and specific gravity is given. So I am taking final aggregates 30% from the stock A, 30% from the stock B, 40% from the stock C. So what is the final specific gravity? I have to calculate. Let us see. So because stockpile A has only coarse aggregates, let me calculate the bulk specific gravity of stockpile A. How do we calculate? The formula is 100 by 70% by 2.720. 70 by 2.720. You will get the specific gravity of stock A. So if you want to calculate the specific gravity of stock B, it has both coarse and fine. So 100 by 50 by 50 is the percentage of coarse fraction and the specific gravity is 2.670 plus 10 is the percentage of fine fraction and the specific gravity is 2.570. You can calculate this. And then as far as stockpile C is concerned, we have 100 by 30 by 2.730. Okay. So now we have a specific gravity for stock A, stock B and stock C. If we want final specific gravity, so stock A this much is the specific gravity, B this much, C is this much. So if you want to calculate final specific gravity, 100 by, what is the percentage from stock A? 30% divided by specific gravity is 3.885 plus from stock B the percentage is 30% divided by the specific gravity is 4.421 plus from stock C the percentage is 40 divided by 1.820. If we calculate, we will get the final specific gravity. So that is for coarse and fine. If we talk about the filler, so these are called as the density bottles. So to calculate the specific gravity of filler material which is passing 75 micron, we usually use density bottle. And calculating the saturated surface dry weight of this filler is extremely difficult. So we calculate the apparent specific gravity. If it is apparent specific gravity, it is completely easy. It is exactly like cement or soil. So according to American standards or according to IS standard also we can actually calculate. So there is no new process. And the important discussion is on the behavior of granular materials. Okay, so granular materials are stress dependent. That means if we have aggregates, these aggregates are actually individual particles. So when I apply a wheel load from the top, how these aggregates are going to respond depends upon their pressure from the side and the bottom. Okay, if there is no pressure from the sides, these aggregates will be deformed very quickly. If there is a pressure from the sides, they will not be deformed that much quickly. That means they are stress dependent. They are not that much temperature dependent like bitumen. Bitumen, if you increase the temperature, it becomes very soft. But aggregates, if you see any stones on the road, they are not going to change their shape just because if you increase the temperature. Okay, so their stiffness, aggregate stiffness is a function of stress, especially the confining stress. So the behavior of these aggregates is actually explained by the shakedown theory. Okay, so let me take this graph and explain. So if you understand this, that all the regions will be understood. So let us say you have aggregates now and a wheel load is applied from the top. Initially my load is very less, let us say 20 kilonewtons. So when I apply the load, so vehicle has moved from here and it has already moved. So for 5 seconds the load is applied. So after that what happens? Let us say when the load is applied, aggregates might have deformed a little. Immediately after 5 seconds what happens? They will come to the original position. because the load application is very lesser in time and the load applied is also very less. So that stage is called as elastic stage. That means the load whatever is applied in this direction, in the return also in the same direction. That means there is no energy loss. This state is called elastic. Now what I am going to do is I am applying 40 kilonewtons load. That means I am increasing the stress. I am increasing the load. What happens then? Let us say this is what the load is applied. So when I release the load, it is not following the same path. It is not in return. It is not following the same path. What is happening? It is returning the different path. That means there is a gap. This gap indicates that there is a deformation in the material. So it is coming into the different path. Now what I am doing? I am again applying the load. Again I am applying. So it will go, it will go, it will go till here. So if you remove the load, what happens now? Again coming into the different path. So what happens in each stage? There is an accumulation of some strain. That means strain is keep on increasing. That is what called as plastic strain. That means this strain cannot be recovered. Once it is formed into this, let us say, shape of this deformed shape, it will not come into, this is a virginal, let us say, virginal condition. This will not be coming back. This is called plastic strain. So if you keep on increasing the load, let us say to 100 kilonewton, for 1 month I am keep on increasing the load. So this plastic strain may increase, but it will reach to some certain stage that beyond that it will not increase, because now all the strain that has to occur, it has come. So this plastic strain from then onwards it will become constant. After that what happens? If I still apply more load also, it will start behaving as elastic material. Okay. So this stage is called as elastic shakedown. So after particular limit it will again behave as elastic. Okay, if you could see here, the region 1 is elastic. Here we have applied very less stress. Energy applied is released. So whatever we have applied, that energy has released under unloading. And if you come to the second stage, which is nothing but elastic shakedown. So here the load we have increased further, then particles have tried to adjust among themselves, deformation is observed, plastic strain has starts to accumulate. So after particular amount of cycles, plastic strain will be remained constant, then the material will start acting as a elastic. So there is third stage. That means I have further increased the load. What happens if we further increase load? If I further increase, previously they used to adjust together, they used to compact. But now if I still increase the load, what happens? Then they are subjected to low level of abrasion because there is no space now. So they will be rubbing each other. That is called abrasion. So there will be little loss in the material because they will be crushed each other. It will happen for particular amount of cycles. Let us say 10 vehicles, 20 vehicles. But after 100 vehicles, what happens? Again, this will become constant. Then it will start behaving as elastic in nature. Then later what happens? In the last stage, if I further increase the load, now there is no chance that it can take. So their abrasion has also started, material has started coming out. Then if you further increase the load, there will be a complete failure of the specimen or lot of crushing. This stage is called as plastic strain until failure. Okay. So these are the 5 stages you can see here. This is the final stage. So this is a very complex behavior. If you understand, these stages are very complex in nature. But if you take the first 2 regions, what are the first 2 regions? So if I apply a load, strain starts increasing. There will be a plastic strain. After a particular amount of load cycles, this plastic strain becomes constant. So after this number of cycles, what happens? Material starts to behave as elastic. So in the another region, there will be more strain, but after a particular number of cycles again, it will start acting as a elastic. But in the region 4 and 5, it will keep on increasing, and in the region 5, actually material will fail. Understanding these two regions and analyzing is very complex in nature. That is the reason why we always assume our material is in region 2 and 3. That means granular materials, we assume that they will behave as elastic after a particular number of cycles. So based on this concept only, we will be calculating its modulus value also. Okay. If you see here, let us say there is a specimen. This is the specimen. Okay. There is a confining pressure from the sides. From the top, we are applying some vertical pressure. It is, you will apply for once. Load is applied once. You will not stop. You will give some rest. Again, you will apply. So this is called repeated triaxial. So you will be keep on applying. So let us say first time you applied the load. So you stopped the load. Then what is happening? Material is recovering, but it is not recovering till initial. There is some gap. This is what deformation. Again you are applying the load. You have applied the load and you release the load. Then material starts to recover. It came till now. That means again deformation increased. Again you are applying. So what happens, as you see, strain is keep on increasing. After particular number of cycles, this plastic strain becomes constant. So this is what called elastic strain. You know what is the applied load? That is called as stress, deviatic stress. You know this strain, recoverable strain. So modulus is always stress by strain. So this is what called as resilient modulus. So sometimes it is not that easy to calculate the resilient modulus. Most of the people might or might not have the facility in the laboratory. So that is the reason why there are few models, okay, to understand the resilient modulus. If you see this model, resilient modulus is a function of sigma 3. Sigma 3 is nothing but confining pressure. And here also resilient modulus is a function of theta. Theta is nothing but bulk stress. Sigma 1 plus sigma 2 plus sigma 3. And here resilient modulus is a function of both theta and sigma d. Okay, how do we arrive with these three models? Let me give a quick overview. Let us say, so we will be performing repeated triaxial test. Let us say you have taken a specimen like this, okay, specimen of height h. Initially you will take 20 confining pressure. That means horizontally you are applying 20 pounds per square inch, let us say. This much sigma 3 you are applying. So you will apply some deviatic stress. Let us say this one. When you apply this 20 lateral, 1 deviatic stress, what is the deformation? Initially H1 is the height of the specimen. After applying the load, this might be converted into H2. So this is called as deformation will be H2 minus H1. Okay, this is a deformation. Strain means H2 minus H1 by H. So what is the change in deformation corresponding to the initial height? This is the strain. You already know the strain. You know the applied deviatic stress will be sigma 1 minus sigma 3. Okay. So if you know the stress, if you know the strain, ratio will be resilient modulus. Again now for the same confining pressure of 20, you will change this deviatic stress. Then you will calculate the deformation, strain, resilient modulus and all the parameters. Again you will change the confining pressure. You can also calculate the stress invariant, which is nothing but the theta, sigma 1 plus sigma 2 plus sigma 3. So now you have the data of all sigma 3s, all sigma d's and also stress invariants. So you can plot a graph like this. Okay. So this is a resilient modulus, this is a stress invariant. So from this graph, you can actually create an equation. Okay. So this equation, resilient modulus as a function of what is there on x-axis, theta. Okay, that is how, using a lot of experimental data, people have come across these three models. Okay, this is the end. I hope this week 4 summary has been understood to you. Is there anything else that you all wanted to ask? Yes, please, you can unmute and ask. Yes, sir. Okay. Yes. Okay. Hmm. Yes, yes. For example, if we are going to do on a dense graded, so where the sizes could be from 19, 13.2, ranging to 75 micron. So in those dense gradations, we don't need to test on these 80, 63, 63, 50, 52, 40. So we don't need to select this E, F, G if you see. So we have to select the gradation in such a way that the ranges should be according to our requirement. So if you are doing for dense gradation, if you go for DVM, then you might have 26.5. This is also dense gradation, yet still you can change if you want. So whenever we do for dense gradation, it is better to choose this BC. Let us B gradation 20, 12.5, 12.5 to 10. It is okay. C also we can choose, because you can perform B and C both separately. So you will come to know the abrasion of these sizes and also these sizes. But it is completely of no use if we select E grade. Yes, 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 higher sizes. Yes, sir. Thank you. Is there any other questions from the participants? Okay. Okay, then we'll close the meet. Thank you. Thank you, sir. Thank you for joining all of you. Thank you.